last time we were last time we were looking at these. So we wanted to look at the Barson's sparsifier, and we decided we'll look at this problem instead, which is what they also solve. So if you're given a set of vectors, m vectors in that so-called isotropic position, so there's some vi transpose is the identity, and then from this what you want to do is to find a small set. So m might be large, but you want to find, and you're given this d, you want to find some set of about n times d, n times d vectors, and you're also allowed to assign weights to them, positive weights, so that when you do the weighted sum of just those subset of vectors, you are within like it's still close to being identity, in the sense that it's bounded by identity on both sides with up to a small factor. The factor depends only upon d, not upon n, right? That was the goal, and the exact value of the factor also matters. It's like always, yeah, it's like 1 over 2 over root d square. Okay, so, so the goal was to show that lambda max.
Sorry, what was the VIs again?
Sorry, VIs are just some arbitrary vectors that are given to you with and with the guarantee that if you took the rank 1 matrix of all of them and summed them up, it will be identity.
Okay.
That's it. And now you want to get a smaller set of such vectors with weights, as that it's still close to identity and much smaller. So it was m here, and now you want n times d, where n is the underlying dimension, d is just some arbitrary number, but the approximation can depend upon d. Okay, and the algorithm we said will be of the following kind, that at each step we'll choose one vector which we add, and we'll do this n times d times, and at the end somehow things will be fine, like they will have the right number. So so how does this work? So before doing that, we started looking at this calculus of rank 1 updates. So how does the inverse of a matrix change when you add a rank 1 matrix to it? How do eigenvalues change, and so on? Because that's what the algorithm seems to be doing. It will just keep doing a rank 1 updates to some starting matrix. So we saw this so the general trick of all of this is to just concentrate on the space of the rank 1. It's a rank 1 matrix. It acts non-trivially only on a small space. So you just concentrate on that state and do calculations there. That's the general trick. And using that trick, we saw that that A plus UV transpose inverse, for example, is A inverse minus. We got an exact formula. So it's always defined as long as this term here is non-zero, and it's not terribly complicated also. Okay, and then we also look at the determinant. The determinant will not actually need so much, but it's still good to know. So I'll just compute. I'll just finish this, and then we'll proceed to the analysis of the algorithm. Okay, so we already saw that how the determinant changes under rank 1 update. So now that also tells us. So we can now apply this to the characteristic polynomial. So the determinant of A plus UV transpose minus lambda I is determinant of A minus lambda I times I plus so V transpose A minus lambda I inverse is this. So this is all to the debt here, the determinant of this. Oh, sorry, this is all fine. This is pointless. That's what we have. Yeah. 1 plus V transpose minus lambda inverse Okay. So now this actually is so let's just think about it. So this is just the characteristic polynomial of the original matrix, right? So this is like saying that chi of A plus UV transpose is chi of A times this 1 plus V transpose A minus lambda I inverse. So what is this thing? So now A, so let's say, so now suppose, so this is general. Now suppose
Sorry, what is chi?
characteristic polynomial. So
Okay.
characteristic in lambda. Now suppose that suppose that A is symmetric and U and V are parallel. So U is some S times V, or yeah, U is S times V for some, let's say for some S polynomial. So now let's try to simplify this and that's set up. So see what we get. So then we have that. So what we're getting is that the characteristic polynomial of A plus, so V transpose is the characteristic polynomial of A times 1 plus S times V transpose A minus lambda I inverse V. But A is symmetric, so it has a, so it has an orthonormal eigencomposition. So what does it mean? So A is the sum lambda I W transpose I n, where lambda I real and W I transpose WJ is determinant. So okay, so but then this A minus lambda I inverse can be written as so
Is it lambda I minus lambda 1 by?
yeah. So so we have that the characteristic polynomial of with the rank one update looks like the product of the characteristic polynomial times something which is like a, it's not so bad, right? It's just a sum of rational functions. It looks like V transpose WI whole squared.
Sorry, but doesn't this imply any eigenvalue of A is also an eigenvalue of A plus A's VV transpose?
Yeah, so let's see. So there's a problem, right? So you cannot just substitute W lambda equal to lambda because these terms are blowing up.
Oh, okay.
Right? So let's see what it means. But you're sort of right. So if repeated things will work, but yeah, let's just see what. So let's now see what this means in terms of like. So but note, so caution cannot just substitute lambda equal to lambda. But let's consider a special, consider at least one one case when the lambda is a distinct. So let's, so but let's look at the case. Lambda are distinct, and let's call this function f. What is, let's call this f fva lambda, and consider look at and plot f v. So assume that you have lambda1 bigger than lambda2 bigger than lambda3. Actually, let's say they are distinct, right? So they are all different.
So the above equation is true as a polynomial identity, right? This
Well,
that
it's not a
doesn't care
polynomial
for.
identity. That's the point. The right hand. So yeah,
Okay.
it is yeah, it is true if you clear fractions. Yes, but the right hand side, as it is written, it's a product of a polynomial times a rational function. So if you multiply things out, it will be a polynomial, but it's not a polynomial that necessarily vanishes at lambda.
Okay, so it was never a polynomial identity to start with, right? Even before you
You can make it
assume.
a polynomial identity. That's fine. So how do you make it a polynomial identity? So then there's a chi a, and then there is sum over chi a divided by lambda a minus lambda, right? So now what is chi a? Chi a is just a product of all the lambda a minus lambda, right? Up to some, yeah, that's exactly what it is. Chi a is exactly lambda a minus lambda, the product up to some constant factor.
Yeah.
So then it's a polynomial identity, yes. But then you substitute lambda a on both sides. You don't get
0 is equal to 0.
No, you don't get 0 equal to 0. Well, yeah, I mean, this side is 0 and this side is 0, but it's not like the, you don't get 0. I mean, that's the point. That's what I'm saying. So this side is not necessarily 0 because there are terms here that are not 0. This one term here is not 0.
So then this equation is, so that's what I'm confused about. It's not true as a polynomial even after clearing.
So I just think
Okay, missing
clear out the
something.
fractions. What does it become? So what is the first term? It's chi a.
Yeah.
And then there are n more terms. Each term looks like chi a divided by lambda a minus lambda.
Yes.
But what is chi a? It's a product of the product of lambda a minus lambda.
Yeah.
So just look at any one of those. The lambda a minus lambda factor is gone.
Yes.
All the other factors are there.
Yeah.
Right? Now,
Yes.
now put lambda equal to lambda.
Oh, okay.
Does this vanish? No. That's
Oh, the left hand side is also not vanishing. Then.
Yeah.
Yeah. Okay. Yeah.
Yeah. Okay, so but let's so and here is just another so it's a good question because it's another way of seeing this more graphic. So
sorry, Piyush, what are we trying to prove?
no, we just want to understand what the eigenvalues of A plus SVV transpose. So how do the eigenvalues change? So that's our goal, right? Our goal is our algorithm is that we'll keep adding rank 1 updates to our matrix, and then hopefully at the end we'll have a good ratio between the maximum and minimum eigenvalues. So you want to understand how eigenvalues change when you do rank 1 updates.
Okay.
So we would actually use this in the proof, but it's just good to, and that was this was their intuition. So if you read their paper, they explicitly point out how they how this was the one thing that inspired their algorithm. So this is lambda 1. Sorry, lambda n. These draw 3 lambda n minus 2 and so this is lambda 1. Okay. So let's see. So what is how does this function look? And this is the y. This line is y equal to 0. Okay. So what does the function look like? So and we've got so. So this is a plot of.
Sorry, can you show again FBA lambda? It's what is FBA lambda again?
Yeah, so it's 1 plus sum over I going from 1 to n. Then there is something positive on the different positive numbers on top, and each term looks like lambda I minus lambda.
This is almost like the tan function, like close to the axis is it will behave from plus infinity to minus infinity.
Yeah, so let's just see. So what happens here? So maybe just here. So at lambda equal to infinity, what is it? It's 0, right? Or not 0, it's 1. So the curve looks like this. So here, as it comes closer to lambda n, it goes to infinity. Right? Okay. How does it behave in between? So what does it do in between lambda and so it's the crucial thing to notice that it's always at every point it is actually at every point where it is continuous and differential, it's actually strictly increasing. So as I was saying, it'll go to minus infinity or plus infinity depending on which side. So it starts at minus infinity, and then goes like this. And similarly. Okay. And then finally, what happens here in the last one?
Starts from minus
It
infinity
goes to
towards
0.
1.
It goes to 1.
0,
Yes.
right?
There's a 1 plus something.
Oh.
Okay, so then now in this case, can you tell me about the eigenvalues of what can you tell me about the eigenvalues of A plus S PV transpose?
Interlaced with eigenvalues
Yeah,
of
and this you could have actually proven just without doing all this, right? You could have just proven it by just usual Rayleigh coefficient kind of thing in this setting. But it's good to see this different proof, and it also tells you maybe that you can. So you can take the so this is because it's growing up. You can sort of also hope to use this as a numerical method for probably finding the eigenvalues. So that's the thing that will be used in the proof. But is
so
this
binary search between two consecutive.
Yeah, that is possible. Yeah, but I mean, you can also use it theoretically as a sort of as the value of some kind of like value of this thing as a potential function to see how far you are from a root. If you're, yeah, it's sort of. Okay, so yes, so this interlacing in this case, so we get a different proof of the interlacing. Okay. So the proof will actually be based on, so the proof is that if we are able to find some vector V with some nice properties and the eigenvalues change in some reasonable way. So yeah, so now that we are done with this, let's come back to the proof.
Piyush, is the interlacing also evident from the Rayleigh coefficient? Like I can see
Yes,
all
yes,
the
that's what I'm saying.
eigenvalues will.
Yeah.
Huh?
So the usual proof is via Rayleigh coefficients. It's called the Cauchy interlacing theorem.
Okay. Okay.
But this is maybe giving you more sort of numerical information. It's probably giving you more. So that's.
Okay, I see.
So in particular, the fact that the highest eigenvalue has to be larger is pretty easy, right? From
Yeah.
and then you
Yeah.
can sort of keep proceeding.
Does it give a sense of how the eigenvectors change, or that is difficult?
Yeah, so I mean, you can try to use again the rank one update technology, but yeah, I mean, I haven't done it, but yeah, it probably give you something, but I'm not sure how useful.
Okay, like I am having one sort of difficulty or sort of some geometrical intuition which is not matching up, is that what if S is very, very large? Why is it that the second eigenvalue is not shooting over the first one? Like what if I take V to be the second eigenvector of A?
Yeah.
And I set S to be really large.
Yes, the eigenvectors might move over each other or something like that, but like, yeah, so some other vector might become the eigenvector.
Oh, okay, okay. So then there is no way of tracking these
Yeah.
eigenvectors. Okay, okay. Yeah.
Yeah, so the proof will, so it will use two potential functions just sort of inspired from the previous calculation. So there will be so-called upper barrier and lower barrier. So we have two potential functions. So, so, so the upper barrier
Sorry, Piyush. Yeah, so the algorithm was what again? So
the algorithm, I didn't fully specify the algorithm, but the algorithm was of this form, that you start with a zero matrix, and at each step you add one vector to it, and you do this n
no,
times.
which one
How
do
do
you
choose
add?
it?
How do you? Which one do you add?
Yeah, so this is that is what we will now see.
Okay.
So yeah, so the thing is, you want to somehow add one, so you have some handle on how rank one updates change the matrix. So you want to add one which sort of is doing something, which is making some progress. So the question is what kind of progress, and that is how also see what the vector is. Okay. So this is two definitions. So this is called the upper barriers. So why is the upper barrier? So it's some u that is in this part of the graph here, and so you're looking at u minus lambda I. So and then there's a lower barrier. So let me just use this notation. So this is lowercase, this is uppercase, and here is subscript, superscript. Okay. And what we will so the goal will be to start with some value of u and some value of l. So initially m is 0. So there's some or some fixed matrix. So it's easy to choose some u and l which have this property, and then keep adding vectors while also changing the value of u. In fact, each iteration, the value of u will change by a constant. It will increase by a constant, and L will also increase by a constant. So both L and U will keep moving up while having both these properties. And yeah, and so let me say, so the general strategy is this. Let AQ be the matrix after Q vectors have been added with appropriate weight. Then we will like to ensure, we will ensure that phi u cube of AQ is less than some epsilon u, and phi L cube of AQ is also less than some epsilon L, where this UQ will just be the initial U plus Q minus 1 times. And similarly, LQ will also be delta L. And that lambda max of AQ is less than UQ, and lambda min of AQ is greater than LQ. Okay. So here there are many free parameters. The free, so U0, L0, delta L, delta U, epsilon U, and epsilon L are all free parameters to be chosen. That we can choose. Okay. Okay. And now, but what do we want? So then finally, and the bound we will get, and finally, if we succeed, we have that A times, let's say, n. So let's say A times nd plus 1. So this one. So lambda max of A times is less than U0 plus nd delta U0 plus nd. And so the point would be to keep this. So we would want, so if we can, if we ensure that this ratio is at most whatever we wanted, it's a d plus 1 over d minus 1. In general, whatever we can get for this ratio will be our answer, will be our approximation. So the goal is we want to keep adding vectors in such a way that these barriers change in, so they always remain bounded by epsilon u, epsilon l. So what is this saying? So when is this barrier small? So u sort of is small if u is a sort of far away, it's far away from the, so if it comes very close, then the barrier will increase. Right? So u, this thing remains sort of far away from the top, I can work with. And similarly, L also remains far away. And then if we succeed, we have this kind of bound on the ratio. So the goal is to see for what parameters can we achieve this kind of. And the reason for these kind of, why this barrier, so we have seen that these kind of things we might be able to handle with our rank 1 update machinery. So now let's see what happens. So we now need to analyze how these barriers.
Sorry, what is the condition on lambda max and lambda min of AQ? Why is this condition there? What's
so that is more or less to just make that this thing is corrected. So u has to be above that. So the upper barrier, the u of the upper barrier has to be above all the eigenvalues. L of the lower barrier has to be lower than all of them. And if you have this condition, right, then you have this also.
So then, oh, okay.
So now, so you want to see how the barriers change with rank one updates. So let's look at the upper barrier first. Okay, so so let's look at phi of u plus delta of a plus some t times VV transpose. So this is what we want. So what is this? So this is by definition. So it is 1 over u plus delta minus lambda I of a plus t transpose. Right, I going from 1 to n, which is the same thing as trace of u plus delta times I minus a plus t VV transpose. So the trace of the inverse of the matrix. So trace is of the inverse of this matrix. Okay. So this is just, this is clear, right? So the sum, so this because so this is just sum of eigenvalues of the matrix, which is u minus. So so what is this? This is a trace of ui minus a inverse. So this is not. This is just okay. But we know. So this we sort of know how to handle it. So with the rank one. So with the inverse. So this is like. So this is like a minus u plus delta I. So this matrix. So this is like. Let me just drop this delta for now and just do it for you, and then we will substitute it later. This notation will just become too complex. Okay, and so this is just trace of ui minus a inverse. So I'm just applying the Sherman-Morrison formula. My plus t times so so b, so let me just b inverse plus t times b inverse VV transpose b inverse over 1 minus t times b transpose b inverse. Okay, but trace of b inverse is exactly phi u of a. So plus trace of this, but if you think about it, this is the trace of that is just so it's 3 times v transpose. So is that fine?
Yeah.
So the point is that this trace of v transpose b inverse is just trace. So you just do use cyclicity of trace. It's just v transpose b inverse b inverse, which is now this is a number. Okay. Okay. So yes. So in rank one update seem to not. So it seems to be manageable. So let's now put our u plus delta here. So u plus delta. If I put a u plus delta, then a plus t b transpose. So it will be phi u of a. So yeah, so because now this is by the way a positive term, okay. And plus, so what is this? V transpose t times. So let me write it like this. Let's divide by t and get like 1 over t minus. So now it's V transpose u plus delta I minus a to the minus v and 1 over t minus v transpose u plus delta I minus a inverse v. So note that if delta is bigger than 0, u is bigger than lambda max a, then this phi u of a is bigger than phi u plus delta. Okay, and right, that is clear, right? Remember that the form of this. So if I increase u, this value only decreases. Okay, so
If we use less than lambda I, then okay, no. No, sorry.
So use so now so if this thing, if t is such that if t greater than 0 is such that one over t is greater than v transpose. So it's actually strictly v transpose u plus delta I minus u minus v divided by this phi u a minus phi u plus delta a, okay, plus v transpose u plus delta I. So this we will call u. This will be defined to be u a u plus delta. So if it is, if t is such, then phi of u plus delta a plus t v transpose is less than phi of u. So this is just algebra. So let us see what we did. So we got this expression that the u plus delta. So we have changed we have increased the threshold slightly, and also done a rank 1 update. And then we're saying that now if we look at this phi of ua minus phi of ua minus phi, so this expression is just coming from the previous one, and now we have this t. So just notice what is the condition that this should be less than this. So everything here should be negative. So that just by looking at the inequality, if t is positive and it is such that that 1 over t is bigger than this thing here, okay, then, and this number we are defining as a equals delta v, then you have that the potential value is dropped. Remember, our goal is to keep the potential value smaller than some epsilon u. So if the original one was less than epsilon u, so this u is not changing, right? So this is the same u. So this epsilon u remains the same throughout the process. So if we choose t like this, we would have, and if the condition was holding at the previous step, it will continue to hold at the next step. The important thing is that this holds for all t which are bigger than this. It means that it holds for all t that are small enough, right? So one thing is, is it true that when you choose that t, the u plus delta so there's another condition that we wanted, right? That u plus delta should be bigger than the largest eigenvalue of a plus t vv delta. So this is another condition that is implicit that we want, and that will also be satisfied by this. So let's leave that as an exercise for now, but at least let's just keep track of this condition. So here is one condition, and this condition, if you think about it, it's linear in vv transpose, right? So this, if I write it as a trace, I can just write it as a trace of so the whole thing is just a trace of this. Right? So it is a linear function of VV transpose. This is something to just remember. Right? Okay. So we also remember, however, that we also have to so the thing I want to claim is that this is also this condition, this if T satisfies this condition, then it also satisfies this, but let's not worry about that right now. But let's just look at the lower value. The lower value will be a similar
Till now, epsilon u hasn't shown up, right?
no, yeah. So it'll show up later. Yeah. So right now we're
Okay.
just hoping to keep things small, and then
Yeah.
Um, yeah, so let me just do the lower barriers. So it's phi L. So what is this? So this is again a trace of, so again the same thing. So trace of A T minus Li. Okay. And again, so by the Morrison formula, it is so again D inverse minus T times, so this time is a minus sign, T times B inverse PV transpose T inverse 1 plus where which is equal to phi L of A minus V transpose. Again, so I'll again do the same thing. So 1 over T plus V transpose. Okay, so this phi of L plus delta of A plus T transpose is again phi L A plus phi L plus delta A minus phi L A minus V transpose A minus U L plus delta I minus 2 plus transpose. So assume that delta is small enough that A is bigger than, so L plus delta I. Remember that L is strictly less than the smallest eigenvalue of A. So certainly for there are small enough. So because L is less than lambda min of A, this is true for all, for small enough positive delta. So this is one condition, and the other condition is again on T. So again by the same kind of thing. So we want to say that this phi L is also decreasing, and 0 less than 1 by T is less than V transpose A minus L plus delta. So the point of this is to make sure that this matrix that we're inverting are all positive definite. So again, notice that this number is positive. The number, the denominator is positive. Okay, so this again we will call this. This is L A L plus delta V. And again, it's linear in V transpose. They're the same. So then what happens? Then the lower barrier is also negative. The lower barrier but note that this is now conflicting. So this requires T to be somewhat large, right? And the previous one requires T to be small. So these are conflicting requirements. The question is, can we find a T and a vector V where both of them are satisfied at the same time? Okay, so let's call this requirement the U requirement. So U requirement and L requirement. And the point is that these two are conflicting. So U requirement requires T to be small. L requirement okay. Okay, so our goal is to find these parameters delta L, delta U, epsilon L, epsilon U, U0, L0. So that at each step, both the U requirement and L requirement can be satisfied for some V and some T. Okay, so let's look at some formal requirement. So let's just see what all we have so far, some of which I haven't explicitly stated. So our goal, so or there's a formal statement so far. Formal statement of so far. So if lambda max of A is less than U, lambda min of A is greater than L, and phi L of A is less than 1 over delta L. So together these two imply that lambda min of A plus lambda min of A is actually is bigger than L plus delta L. Why is that? So if phi L of A is less than 1 over delta L, each term in the definition of phi L A is positive. So in particular, so this means that 1 over lambda min minus L is less than 1 over delta L, right? Which is the same thing as exactly this. So this is a new condition that we are imposing. And T and V are such that, and by the way, this when you have lambda min A less bigger than L plus delta L, then this condition that A bigger than L plus delta I is already satisfied. So and T and V are such that 0 is less than UA U plus delta. So this I didn't explicitly prove, but yeah, this also we have to do. So by the way, so how will you specify this? So remember that so this will be true if 1 over delta L is bigger than epsilon mu, right? So so we'll be satisfied by you just have epsilon less than 1 over delta. Okay. So then this will be true because phi L of A is going to be less than epsilon. Okay. So this is the thing. So these two things. So these were not formally proved above. But let's come to them later, maybe, or have leave it to the next exercise. The same kind of arguments we can do that. Right now, let us just say how we find such a. Why is there such a T and a V? So is the goal clear now? What we have to do? So we want to find one T and V so that both these conditions that we have asked for are satisfied.
Yeah. So this epsilon L is actually for all purposes just 1 over delta L.
Yeah, that's true.
Okay.
Okay. So by the way, so how what now we are in, so we want to say that there is some vector for V for which UA is less, so there's some T for which UA is less than 1 over T, which is less than LA, which is less than LA of V. So what is one kind of thing that would immediately imply such a thing? So there are many vectors V, right? There are m of them.
Some average thing.
Yeah, exactly. So if the sum over all the vectors of the UA was less than the sum of over all the vectors of LA, then we would be done. Because then in between there must be a real number. We'll just call that number 1 over T. And this is also showing why the weight is needed, right? So you don't know where this number is. That's not we are going to be able to say, but it's some number, and that's the T value. So so this is called, let me call this a joint requirement. Joint requirement will follow if we show that the sum LA L plus delta L VG J equals from 1 to n is less than J equals from 1 to n. L A U plus delta U VG plus 10, because then you just choose the vector. Yeah, so then just choose the, so this means that if you look at U minus V, the average is negative, so there's at least one vector which keeps this, and so you just choose that vector. Okay. Then so, a pair V comma T as required will exist. So now we have to, so now we want to prove star. Okay, so okay. So any questions so far?
In this barrier functions, this upper and lower barriers that were defined,
Yeah.
they like how do they help to track
So,
so
how do
okay
you, so how will you find the vector? So you will just compute this U, which is in terms of the barrier functions, and for every vector, and take this and like just, how will you find such a V? So you will have to compute these for every vector V. How will you compute this? So you have to compute the barrier function, and
but this L thing doesn't have, like, where is the barrier function in this L? In the definition of L, there was some phi L. Okay.
So the capital L is based on this lower barrier, and the capital U is based on the upper barrier.
Okay.
Okay, so now let's just so this is more or less just a calculation. So let's just compute a sum. So just let's check, so look at the sum of the upper barrier. So what's the sum of the upper barrier? So let me just yeah, okay, yes, so let's do it like U plus delta U of Vj. So what is this? So remember the form, right? So it was linear in V transpose. Everything else did not depend upon V at all. So this whole thing will become trace of so U plus delta U times I minus A minus 2, and here there is a sum over J of Vj transpose divided by this by U A minus by U plus delta U. And plus, so this whole thing is in the inside the trace. Here again, U plus delta Ui minus A inverse times summation j vj transpose. Okay. But what is summation j vj vj transpose? Is identity, right? So this whole thing is right. So it's but the point is that is that vj is identity. That was the condition on the vectors. So this becomes identity. So now we are just doing trace of these kind of polynomials and this barrier function. So I'll just write it out like everything without the matrix, just in terms of the eigenvalues. Okay. So everything is about a. So here I have I 1 over. Let me just. So this will be u plus delta u minus lambda I. So lambda I is always of a. Okay. A minus 2. And here, so it's u minus lambda I a inverse minus u plus delta u minus lambda I a inverse, okay, and plus summation u plus delta u minus lambda I a inverse. So this simplifies, right? So what does this simplify to? So here you have -2. And what is this? So it's 1 over u minus lambda I minus 1 over u plus delta u minus lambda I. So this becomes delta u summation over I u minus lambda I inverse u plus delta u minus lambda I. Plus what is this? This is just nothing but phi of u plus delta u. Okay. And this thing also, if you notice, each term here and the numerator is what? Each term in the numerator is
Positive.
no, positive is fine, but I want to compare the numerator to the denominator. Is the numerator smaller or the denominator? Just look at term by term.
But the
Denominator is small.
is smaller.
Each term. So if you just look at the ith term, you get u minus lambda I. Their denominator. The denominator is. Each term has a denominator, and the denominator of the numerator is larger than the denominator of the denominator. Okay. So,
Yeah.
so this is less than 1 over delta u, the first one. And the second one is less than, so plus phi of u, right? Because when you increase the u, the barrier can only drop when the matrix is held fixed. For the upper barrier can only drop. So, but this is less than 1 over delta u plus epsilon u, right? Because assume when so the sum of the upper barriers is at most 1 over delta u plus epsilon u. Okay. What about the lower barrier? So it's a similar kind of calculation, and let me. So maybe I'll skip some steps here and just give a final answer. And boring with this subject. So this. If you do, you will find that this after like again some simplifications is exactly 1 over delta L minus minus phi L of A plus summation I lambda I A minus L inverse times lambda I A minus L minus delta L minus 2 summation over I lambda I A minus L inverse minus L minus delta L inverse. This is my, so the difference is that here there is a -2, here there is a -1. That's the only difference between these two. And plus delta L times summation over I lambda I A minus L inverse lambda I A minus L minus delta L. So the denominator here is the same as the sum here. Okay. And notice that, so this is equality. So far, it's everything is equality. There will be no estimates. But now note that this lambda I A minus L inverse lambda I minus L minus delta L inverse whole squared is less than, so by Cauchy Schwarz or Holder summation lambda I minus A minus L inverse times summation lambda I minus L inverse times summation inverse lambda I.
This should be -2, right?
What?
Summation lambda I minus L whole power minus 2.
Correct. So yeah, so you just
No. Okay. Yes. Okay.
Yeah, so you just take the square. Yeah. It's the crucial point. Yeah, the point is that you want to compare to this term. So you break it up slightly differently. So you break up a square root of inverse of lambda minus L inverse. Okay. So this is to there. So when you so this so what does that mean, right? So let's just give me 1 second. Okay, so we have this. So this would imply what? So this would sorry, this was not plus. This was a minus. So now the yeah, it was plus, then we would have just ignored it. So if it is minus, so now we have to look at what this thing is. So we are getting that. So yes, what are we getting? So we are getting that this so we have that this summation over I lambda inverse lambda minus 2 divided by summation over I lambda I minus one is less than is bigger than is bigger than so same things, lambda I minus L. And this thing, right? This phi, this is like just phi L divided by phi L. Okay. Okay. So and notice that phi L of A is less than epsilon. So this is bigger than. So just copy. So epsilon L. Which is bigger than delta. When 1 over epsilon L is bigger than delta L, it's the same thing as saying that delta. Yeah. The same thing as saying that 1 over delta L is bigger than epsilon, which is the condition that we have. Right? So remember that we had put in this condition that 1 over delta will be at least epsilon. Okay, but that, what does that mean? That means that this part is non-negative. Okay. So substituting. And the summation over L A delta plus L B J goes from 1 to n is bigger than or equal to 1 over delta L minus phi L of A, which is bigger than 1 over delta L minus epsilon L. So provided, so what are the conditions that we needed? Provided that phi L of A is less than epsilon L and 1 over delta L is bigger than epsilon. Okay. So so the left hand potential function, the sum is bigger than 1 over delta L minus epsilon. Right? And the right one is at most 1 over delta U plus epsilon U. So what we need, so we have the summation of UA U plus delta U J is less than 1 over delta U plus 1 over plus epsilon U and summation J plus delta N J is greater than 1 over delta. So we need that 1 over delta L minus epsilon U must be bigger than 1 over delta U plus epsilon equals to. And now we can get the conditions. So this is another. So the conditions. So we have added another condition here that along with this delta L, epsilon L is less than equal to 1. right? So this one, we also added this one. So now that we can set parameters. So now set parameters as well. So this is the thing which requires some optimization, and they just sort of yeah. So we start with, so the first matrix. So we start with matrix A0, which is the 0 matrix. Okay, both lambda maxes and lambda min are both 0, and we set delta L equal to 1, epsilon L to be 1 over square root d. Okay, delta U to be square root of d plus 1 over square root d minus 1. So notice that delta L epsilon L is less than equal to 1. So satisfied because d is greater than, and epsilon U to be 1 over root d times root d minus 1 over root d plus 1. Okay, so yeah, so the point is that 1 over delta L minus epsilon L is like 1 minus 1 over root d, and 1 over delta U plus epsilon U is equal to root d minus 1 over root d plus 1. So this is what is like root d minus 1 over root d. So this inequality is true. And then we have to set L0 and U0 also. So L0 is set to minus n over epsilon L, which implies that phi L0 of the 0 matrix of A0 is what? So it's so what is it? What is the lower value? So the initial matrix, all eigenvalues are 0. L is minus n over epsilon L. So each one contributes exactly n over epsilon L. So this is epsilon L. And you set mu0 u0 also to be n over epsilon mu. So again, it's bigger than all the eigenvalues, which is 0, and that implies that at the beginning, at least, again you have this. So you start off in the correct setting. You start off. So when you start with the matrix, you have that the barrier functions have the right conditions. The delta L's and delta U's are all fine. So as you keep continuing this, these conditions remain valid. That's what we have shown so far. So, and yeah, so then now, so is the construction clear now? So you start with A0. You set delta L equal to 1. So you set delta L, delta U, epsilon U, all these quantities. The point is that all the conditions that we required are now satisfied for these choices. And so now what you do, at each point you compute this. At the current value, you compute these L, sum of the L's, and or well, you just you know that the sum of, because of this condition, the sum of the L is at least the sum of the U's. So there's at least one vector for which the sum of the L's is for which the L value is bigger than the U value. So you choose that vector along with the corresponding T that is given by. So the T has to lie between. So remember, right? So we had to do so the joint requirement to satisfy this joint requirement. Where is the joint requirement? Yeah, so we choose V to satisfy the joint requirement, and then with all these conditions that we have, we show that the potential function remains bounded with epsilon L, epsilon U at the next step, and also yeah, and with the choice of T, so you always have these bounds. So after you update L0 to L, so Okay, so yeah, so the algorithm would be start with yeah, actually, I think I messed up something very early. So it was some q minus 1, which should just be q. So at each step, you're adding this term to the potential function. Start with a0 equal to the 0 matrix and u0 l0 delta l delta u epsilon l as above for q going from 1 to n times t. What do you do? Compute L of this A and LQ Vj. So LV compute the above. Above there exists a G and P positives of that. So A and Q is bigger than P is bigger than UA UQ G. Set AQ minus 1 plus P times Vj. Okay, so that's it. And then what is the so the above so we will then have lambda max of AQ is less than BQ lambda min of AQ is less than LQ. Sorry, let's click on LQ and phi UQ. And so lambda max of A and D over lambda min of A and D minus 1 is less than yeah, so what is it? So it is this so you is yeah, so it is like this, right? So it's u0 plus n delta U, 0, which is what? So n over epsilon. N over epsilon U. So 1 over epsilon U plus delta U minus 1 over epsilon L plus delta L. And this d times d times. And this we just now do it. So delta U. Yeah, so this yeah, I will just after substituting. So the only thing that I sort of just know that we did not explicitly argue about that lambda max of A but the same, but yeah, it's not hard to argue that this, given all the things you have done. So this will be an exercise. So any so this will be an exercise. So this will be so sort of, yeah, so fill in this gap. Okay. So I mean, the thing is, yeah, it should not be surprising that this is true, because I mean, you're looking at this barrier and the barriers are themselves not changing. If ever you cross, the barrier should just blow up, and nothing like a blow up seems to be happening in whatever you're doing. So that's roughly the argument you have to make precise. So right, whenever if it does cross, right, so then the barrier will just blow up at that point, and that does not seem to be happening. So that's the only thing to make precise. So any questions about this? So just let me just put the algorithm. Okay?
So does this need, I mean, I'm not fully sure I understand the calculations fully, but does this need this summation VV transpose to be just greater than equal to identity?
No, so, well, I mean, the way we did it, it actually required it to be identity, because at every time we were, so in the L, yeah, so because this same kind of calculation will be done for L also, right? So that step I just skipped and I just wrote down the final answer.
Okay.
So just that would not, you know. But
Is
if you
there,
have
is there,
two-sided bounds, you could still make it work, right? By you will get some different condition. Yes.
so like intuitively this potential function picks out a vector and a t which will have the least change in the max and min eigenvalues. Is that?
No, so it's not least change. Yeah, so I don't think it's just least change. Yeah, it's so it's right. So yeah, so this is more like, yes, you're sort of you're more like committing to making progress. So at each step you want to do the following. You want to, so you have some current maximum value and current eigenvalue. You want to move both of them such that the lower bound on the so the lower bound also moves by a constant and the upper bound also moves by a constant. Both move by a constant. You want to move it in such a way. And there's one vector which achieves it at the same time. That's the point.
So move means multiply by.
No, move as in add. Like, so lambda. So that's the point. Right? So there's this. So what is changing? All the parameters remain the same. Only these upper bounds, these LUs, these LQ and UQ are changing. Right. So the qth matrix, its eigenvalue is bounded above by U0 plus Q times delta U, and this is. So you're sort of moving both of them by constant distance. And if you keep moving things far away, so they start at 0, and then you keep moving them far away, then they start coming close, right? I mean, like if you take two numbers A and B and you just add a huge, like you just keep adding the same number to both of them for a long time, the ratio sort of will start converging to the limit between those two numbers, like the things that you are actually adding. So that's.
Okay, somehow the geometry of this thing is lost, or I don't like. It's like I thought we will look at M and then look at what space is not being acted upon and try to fill that space up. So this is doing something
Well, I
like
mean,
that, but in a very algebraic way. Yeah.
Yeah. So yeah, it is more algebraic. That is true, and yeah, there might be some